So next I want to look at the more specific case of real-valued functions, and we're going to put the Borel sigma algebra on the real line. And we've discussed the Borel sigma algebra in the previous lecture and looked at some different possible generating sets for it. And now I want to focus on one in particular in order to match things up with one of the definitions in the textbook and have a more convenient generating set to work with. So let's define script R. I don't know if that's like any good way to write a script R, but that's what I've been doing. Define it to be this, the collection of intervals of this form. So infinite extent on the left, and then they stop at a certain point, and they don't include the endpoint. Okay, so let R be that collection. Then, along the same lines as in, let me look this up. Along the same lines as in lemma 1, 2, 11, although when I looked there, I actually couldn't see it there. Specifically, the result that I want is not there. So this is like lemma 1, 2, 11. The Borel sigma algebra on R is generated by this collection of intervals. Okay. Okay, let me give a little bit of justification for this. So I think last time what I justified, or what I sort of half justified and then pointed you to a Stack Exchange post to see the details about, we said that the Borel sigma algebra on R so this is last time. We said that the Borel sigma algebra on R can be generated by I think what I called I, the set of open intervals. So where I is just open intervals. Now I claim that, so I'm going to use this as kind of a starting point to try to prove that the Borel sigma algebra on R is generated by on the reals is generated by fancy R here. So first I'm going to claim that if you take these things, then they are definitely in the Borel sigma algebra on R, and that's because the elements of this are all open sets. And the Borel sigma algebra on R is the one generated by open sets. So they're actually in that generating set, the original one that we used to define this. And on the other hand, we have the collection of open intervals is contained in the sigma algebra generated by fancy R here. Because, so to convince you of this, I have to take an interval and show you that it can be written as countable union of countable intersections of countable unions of countable intersections of complements of countable, etc. Of things in R, right? That's pretty much what I have to show. So let's say I take an open interval AB. Well, here's a start. I can write it as, let's see, go out to B and then intersect with this one, right? You can write it like that. And this is in R, but this one might not be. But I claim that it is because it's the complement of that. Okay, but that might not be in R, but I claim that it is. Because, let's see, it's a countable intersection. So it's an intersection of the a plus 1 over n's, like that, running over all natural numbers n. So the argument goes like this: take any a and b real numbers, then given one of these is going to be an element of script R, which is defined up here. And so the countable intersection of them is going to be in the sigma algebra generated by script R. So this is in the sigma algebra generated by script R. So is the complement is in here. And so is this intersection of two things, one of which is in script R itself, and the other, which we just argued, is in the sigma algebra it generates. Okay, so altogether, these facts tell you that, so this fact tells you that the sigma algebra generated by this is a subset of this thing, right? So let me put it this way. Here, this tells you that the sigma algebra generated by fancy R is a subset of the Borel sigma algebra on the reals. And this tells you that the sigma algebra generated by fancy I, which is the Borel sigma algebra on the reals, is a subset of this thing. So that's what these tell us. So that's both inclusions, and that tells us that this equality. Okay, so great. The Borel sigma algebra on the reals is generated by this pretty small collection of sets. I would say small compared to taking like all the open sets. This looks pretty manageable. So given this theorem that we proved in the last video, that it's enough to check for measurability of a function on a generating set, this tells you that if you have a real valued function, it's enough to check for measurability by focusing on preimages of sets of this form. So let's write that down. So let x A be any measurable space. So x is a set, A is a sigma algebra. Then if you have a function f from x to r, so real valued, if you have a real valued function, then f is, let me be clear about what I mean by measurable. A, comma, Borel sigma algebra on R, measurable, if and only if the preimage of any one of these kinds of open sets, one of these kinds of Borel sets, is a measurable subset of X. So if and only if the preimage of this kind of thing is in fancy A. For all there. Yeah, so another way of describing this, so this set here, this is the set of points in the metric space, or the measurable space, maybe not metric space. These are a set of points in the measurable space X, such that f of x is less than c, right? So this is a nice way to describe measurability for a real valued function, assuming you're using the Borel sigma algebra, which is typically what we'd use. This is measurability for a real valued function. And what I'm giving here is definition 2.1.1. So that was actually the first definition in the text, is if you have a real valued function, then it's called measurable if and only if, for any given real number c, this set is a measurable set. All right, but now we're seeing that this is a special case of the original general definition 2.1.3 here. And by the way, there's a theorem in between definition 2.1.3 and definition 2.1.1. There's theorem 2.1.2. And our setup, our way of doing things, especially with this theorem 2.1.L1, makes that theorem 2.1.2 automatically finished. So we're through that as well. All right, I think we're now ready for an example in this more specific setting of real valued functions. So let XA be any measurable space. So A is just some sigma algebra. And let's fix any measurable set. So any A in script A. then there's a function we can define, which I'll call I sub a. This is sometimes called the indicator function on a, and it'll be a function x to r, real valued. And here's the way it works. So for any point x, it either gives you 1 or 0. And what it does is it lights up whenever x is in the set A, and it turns off if x is not in A. So it's an indicator function. It indicates whether or not points are elements of the set A. Sometimes it's also called the characteristic function of A, of Roman A here. Then I claim that this is a measurable function. So IA is measurable, and by measurable I mean this style of measurable. So to see that this is true, you have to, so if I were using the original definition to see that this is true, I'd have to consider an arbitrary Borel subset of the real line, right? An arbitrary Borel measurable subset of the reals, and then think about its preimage. Luckily, I don't have to do that, really, thanks to what we just went through, which is it's sufficient to look at these. So let C be a real number. Then what's the preimage of this interval running up to C? Well, it depends on what C is. So if C is negative, or even if C is 0, considering that, even if C is 0. So let's see, there are 3 possibilities for what this is. If C is negative or 0, then this is the empty set actually, right? Because nothing maps to something less than 0. The outputs of the indicator function are just 1 and 0. On the other hand, if C is is greater than 0 but less than or equal to 1, then I get something. And if C is greater than 1, then I would just get everything, right? Because then for this preimage I would get everything, because every point in the set has the property that the value of the indicator function at it is less than C when C is greater than 1. And what goes in the middle here, when C is in between, you just get the points that are not in A, right? So the complement of A. Okay, so this is a really simple, the most simple situation basically that you can have. There are only 3 possibilities for the preimage of one of these sets. And all we have to do is verify that all 3 of these are measurable subsets of X. And they are. This is always, and this is the complement of something that was assumed to be measurable. So you see why this was important? If we had not assumed that A here was, if we had just let A be a random subset of capital X, then this wouldn't have worked. The indicator function would not necessarily be a measurable function. But since we assumed A is a measurable set, the complement here is measurable, and we have a nice proof that that the indicator function on A is a measurable function. So the indicator function is a really, really simple example of a measurable function. And what makes it a really simple example is that it only has 2 possible outputs, right? It either outputs 1 or it outputs 0. So that helped make it really easy to think about what are the possible preimages. So let's look at another example, which is really simple for the same reason. Let's think about what are, if we have a measurable space X, what are all the measurable functions that have only finitely many possible outputs? So time for a definition. Let X be any measurable space, then we're going to say a function f from x to r is simple. We'll call it simple. So this is our official definition of the adjective simple. If and only if f is a measurable function and has finite range. So f is a measurable function and has finite range. So the range of f is the collection of outputs, where a simple function is one that has that being finite and is measurable. Okay, so what are the simple functions? We can actually describe them all pretty explicitly. So suppose f is simple. Suppose f is simple, and let's say that C1 through Cn is the range of f. So I usually write ran f for the range of f, or the image of f if you prefer to call it that. So these are all real numbers, C1 through Cn, and there's finitely many of them. And I'm assuming they're distinct. So although with this set curly braces notation, they could be non-distinct, and that would still that would not harm this equality. Let's assume they're distinct. Then each preimage of each one of these numbers. So let's give these names. Let's call them a sub i's. So these are going to be defined to be the preimages under f of these singleton sets. A sub I is all of the points in x, in big X, that map to this exact value, c sub I. Then these are all measurable. Yeah. So why am I saying that? I'm saying that because f is simple, so that means it's a measurable function. And here I'm taking the preimage of a Borel set. A singleton of a real number is a Borel set, right? Think about why that is. So here's my answer. They're closed. Closed sets are Borel sets. So these are all, these are all measurable. And you can, assuming these are distinct, you can write f as basically a linear combination of the indicator functions for these. So C1 IA1 plus C2 IA2. So then we're seeing that every simple function is actually a linear combination of indicator functions of measurable sets. So that's a nice explicit description of the simple functions. Maybe a comment is needed about why this equality holds. So to verify that these two functions are equal, we should consider an arbitrary point in big X. If you take a point in big X, then it is going to be in exactly one of these sets a sub I. It's definitely in one of the a sub i's because f of it is going to be one of these numbers, right? And it cannot be in more than one of them because f of our given point from here cannot be more than one of these numbers. I'm assuming they're distinct. So any given point in the domain here is going to be in exactly one of these a sub i's. And so if you evaluate the right-hand side at that point, all of the indicator functions vanish except for the one that that corresponds to the set that has that point. and then you're just left with C subscript whichever was the correct output for f. So pretty straightforward to check this equality. And another comment is, actually what we've done is we've described what all the simple functions have to look like. They have to look like linear combinations of indicator functions of measurable sets. But we have not verified that anytime you do this, you get a simple function. So the collection of simple functions is contained in the collection of linear combinations of indicator functions of measurable sets. But what about the converse? For that, how about looking at it this way? Every indicator function of a measurable set we verified here would be a measurable function. So these individual indicator functions are going to be measurable functions. And so therefore their linear combination is, does that work? It ends up working, but we should prove something like that. So let's build up our toolkit of tools about measurable functions, like that tool, for example. We'll do that in the next video.